Okay, in this example, we're going to take a look at the electric field at a perpendicular bisector for a short rod. And so we're looking at the electric field here at this point P. Now what we have is a rod which is positively charged, and the charge itself is uniform. Point P is located a distance d from the rod, and that the rod also has a total length of L. Now, this problem is a little bit different from the last one. It does have an extra layer of complexity because you're going to notice that as we integrate across the length of the rod itself, the angle between the chunk and point P is changing. Now, this is important because the electric field is a vector, and the angle that the field makes at point P is dependent upon which chunk you're looking at. And what I mean is this: if we're looking at this chunk right here, then the electric field points along this line as we go out to point P and in that direction. So this is the direction of E due to that chunk. Now if we look at the electric field due to an identical chunk located in the mirror image or in the exact opposite place on the other side of the rod, then it produces an electric field which points downward like this. Now, when you're right here at the perpendicular bisector, the electric field is entirely horizontal. So you can see we go from a maximum possible force for the chunk exactly in the middle to a minimum effective force when you're at the ends, because each chunk has components where we have EY and EX, but the EY components cancel each other out because of the symmetry of the rod. All right, and so the only components which are contributing to this problem are EX. Now, just to finish understanding the physical layout of our problem, take note that the net electric field is to the right. So we have the electric field due to the bottom chunk, which points to the right, and then we have an identically strength electric field which points to the right due to the top half. So our total electric field is the total length right here. This is E net. I'll do it in green. Right here is E net. Okay, a little more to do with the geometry. In order to get the X component, this is our angle theta right here. That's going to be the same as this angle right here. And now let's finish just setting up the geometry of our problem and the important points. The distance that we have from the bisector to the end is 1/2 L on each end. And so I think that's it. I think that covers everything. All right, so we're going to start with E is equal to the integral of K dq over r squared. And because we're only interested in that horizontal component, we're going to use cosine of theta. Now remember, the key to understanding these problems, to setting them up and solving them, is to work with charge density. And so just as a quick reminder, remember that we have lambda is equal to Q over L when it's a uniform charge distribution. And in the limit, as the chunks get infinitely small, that becomes dq over our length dimension. Now last time we used dx because the rod was in the horizontal dimension, but now our rod is in the vertical dimension, and so I'm going to say that this is dy. Our limits of integration. Now this requires a little bit of discussion here, because our limits of integration can go from minus L over 2 to L over 2, or we could write, and I'll do this in white, we can use symmetry to our advantage, and we can write from 0 to L over 2, and because of the symmetry, we know that it's going to be 2 times that value. Okay, so I'm going to choose minus L over 2 to L over 2 as my limits, and I'm going to leave it as an exercise to you to prove to yourself that it is the same thing. I want you to actually go through the math and show that they come out to the exact same answer. We have E is equal to the integral from minus L over 2 to L over 2 of k lambda dy over r squared cosine of theta. Now, in this example, r is not equal to x or y. R is a combination of both, so we can't simplify it down to y squared. And cosine theta is also a problem because you'll notice that as we go from one end of the rod to the other, theta is changing. So if we identify our variables and identify our constants, what we get is this. Let's write our list of variables and constants. I think constants will be somewhat easy. L is going to be equal to a constant. D is equal to a constant. And Q is equal to a constant. So these are all constants of our problem. X is also equal to a constant, the distance from the rod to the point in question, but only that horizontal distance. That's what's constant. Now, what's variable? Y is variable because we're actually changing in the Y dimension as we go from chunk to chunk. But this also means that theta is a variable as well. And so one of the things that we want to do is eliminate our unknown variables, and we will eliminate theta because that's easy to put in terms of our one variable that we want to solve and a constant. Okay, so cosine theta, remember, is going to be equal to the adjacent over the hypotenuse. And in our case, to get theta, the adjacent side is equal to d, and the hypotenuse is equal to r. So that means we can write E is equal to 1 over 4 pi epsilon naught, might as well throw that in there now, get it taken care of, times the integral of minus L over 2 to L over 2. Lambda is a constant, so we'll pull that out. And that's going to give us dy over r squared times d over r, which was cosine theta. So continuing on, we get E is equal to 1 over 4 pi epsilon naught times lambda. This d is a constant. We've identified that as a constant because it's just the distance from the rod to that point in space. L and d and x are one and the same value. So we'll pull that d out. And that's going to give us the integral from minus L over 2 to L over 2 of dy over r cubed. Now remember that r is equal to the square root of, it's going to be d squared and y squared. So it's d squared plus y squared. So that's going to make our equation become E is equal to 1 over 4 pi epsilon naught lambda times d times the integral of minus L over 2 to L over 2 of dy over d squared plus y squared raised to the 3/2 power. Now, this is an integral that you can look up, or you can use your calculator if you have a calculator that does the calculus in variable form, like the Inspire CAS or the TI-89. So, you can do that. Okay, so you can look up this integral for 1 over d squared plus y squared to the 3 halves. And what we're going to get here is e is equal to 1 over 4 pi epsilon naught times lambda, which becomes q over L, times d. And then we get from the integral y over d squared times the square root of y squared plus d squared. And we're going to evaluate this from minus L over 2 to L over 2. We can cancel out this d with one of those d's. So we get e is equal to q over 4 pi epsilon naught L times, all right, now y is going to become L over 2 over d times the square root of L over 2 squared plus d squared minus a minus L over 2 over d times the square root of minus L over 2 squared plus d squared. And that simplifies into 1 over 4 pi epsilon naught times q over d times d squared plus L over 2 squared raised to the 1/2 power. Now the important thing to notice here, and if you choose it might be easier to see if we write it this way. If in white I'm going to do the square root instead of using this 1/2. Okay, so if we write it this way, what we see is that this is basically of the form of Coulomb's law for electric fields for a point charge more far away. So we want to check this answer against whether or not this looks like a point particle far away. And one of the ways we can see that is that, when you're up close, the bar has a dimension. But if you stand really, really far away from the bar, it seems to get smaller and smaller, so that eventually that bar just becomes a little tiny point. Depends on how far away you get. As you get further away, in other words, if D is much, much greater than L, the length of our rod, then what ends up happening is this term, this L over 2 term, becomes insignificant. As D gets bigger, this term becomes insignificant, making this whole thing reduced down to E is equal to Q over 4 pi epsilon naught times 1 over D times effectively the square root of D squared plus this insignificant term that basically goes to 0 by comparison. And so this becomes D times the square root of D squared, which is D, or E is equal to Q over 4 pi epsilon naught D squared. And that's the same thing as Coulomb's law for electric fields, which we typically write as KQ over R squared. And so it takes on that same form. So this is a great example of how you can use limits to kind of make sure to use it as a check of sorts to make sure that your work is reasonably correct. Okay, like I said, I leave it to you as an exercise to use 0 to L over 2 as your limits to make sure that your answer works out to be the same.